Our goal is to determine the shape of the path of a projectile moving through the air. So let's look at a specific example. Let's say we launch from the origin at time t equals 0, and our launch velocity, v1, will have components 50 meters per second in the vertical direction and 10 meters per second in the horizontal direction. That means the launch speed we get using the Pythagorean theorem from our two components is about 51 meters per second. And the angle, pretty steep here, we get by doing tangent of that angle is the ratio of our two components. So arctan of that comes out to be about 79 degrees. So we're launching all pretty close to straight up here, 79 degrees, at a speed of 51 meters per second. How fast is that? Well, remember that a meter per second is about 2 miles per hour, roughly. So we're talking launching at around 100 miles per hour, pretty close to straight up. So what happens to an object when you launch that fast at that angle? From the moment it leaves the ground, it's going to be in a state of free fall, which means that its acceleration will be constant and have components in the vertical direction, negative 9.8 meters per second squared. For this example, we'll say that's approximately negative 10 meters per second squared. And it'll have a horizontal component 0. No acceleration in the horizontal direction if you're in free fall. What that implies is that the x component of the velocity is not changing. Therefore, it's equal to the initial, the x component of the initial velocity, 10 meters per second. So throughout the entire motion, you'll be moving to the right at 10 meters per second. Okay, let's draw in what the velocity vector is going to look like at different moments in time. Here's t equals 0, and we'll draw it in at 1 second increments. And at each moment, I've indicated that the acceleration is constant with that negative 10 meters per second squared y component. So in our initial moment, here's what our velocity vector looks like. 50 meters per second is the y component, 10 meters per second is the x component. So if a square here is going to be a scale of 10 meters per second for our velocity vectors, 1, 2, 3, 4, 5. There is our initial velocity. Okay, now 1 second later, if it has been accelerating with these components, the x component hasn't changed, the x component of our velocity hasn't changed, but the y component will have decreased by 10 meters per second in 1 second. So the y component will have decreased from 50 to 40. So our y component is now 40, x component is still 10. So that's our velocity 1 second later. Here was v1, our launch velocity. And that's going to continue. Every second, the y component of the velocity is going to decrease by 10 meters per second, but the x component of the velocity is going to stay the same. So 2 seconds after launch, the y component of velocity will be 30 meters per second. The x component is still 10. Then the y component decreases again and again until at about 5 seconds in, we're going to be near the top of the motion at this point. The y component of the velocity is 0. You're moving only in the x direction. But the acceleration doesn't stop then. It's going to continue to change your y component of the velocity at 10 meters per second per second. So another second later, now we've turned around and we're moving down. And the y component of velocity will continue to decrease by 10 meters per second, while the x component stays the same. So over the course of the journey, if we took a freeze frame of its velocity at different moments, we would see that it starts out very positive, very in the upward direction, and then decreases in the upward direction, and then turns around and starts increasing, becoming more and more negative, aligning itself eventually with the acceleration. Over time, that's what an acceleration tends to do, cause the velocity to align with itself. It's tipped the velocity all the way over to be pointing down in the same direction as the acceleration. Okay, let's map that. Let's say we launch here from the origin at time equals 0, and in our first second, we're moving upwards 50 meters and over 10 meters in the first second, roughly. We know the velocity doesn't actually change just in steps like this. It changes continuously the whole time. But to map our path, we'll look at the position as if the velocity changed in just these steps. Okay, so in the first second, it goes up 50 meters and over 10 meters. So we launch here, then we end up there. 1 second later, so at this time, its velocity, so at time is 1 second, its velocity looks like this. So for the next second, it's going to move upwards approximately 40 meters and over another 10. Then it's going to move upwards about 30 meters and over 10, up 20 meters over 10, up 10 meters over 10. And then it's not moving upwards at all. So from 1 second to 2 seconds, it moves up 40 over 10. From 2 seconds to 3 seconds, it moves up 30 over 10. Then from 3 to 4 seconds, it's going to move up 20 over 10. 4 to 5 seconds, up 10 over 10. 5 to 6 seconds, it's just moving horizontally. It's reached the top of its motion, and for a moment, it's only moving in the x direction. The y component of velocity has gone to 0. Now, it's going to move down 10 meters and over 10, and then it's going to move down 20 over 10, down 30 over 10. So in the next second, it moves over 10, down 10. In the next second, over 10, down 20. Then over 10, down 30. Over 10, down 40. Over 10, down 50, where it impacts the ground. So to sketch that path, is roughly going to look like this. Okay, check out its max height, around 150 meters. How high is that? Well, if a meter is roughly 3 feet for doing an estimate of doing a conversion in your head, then 150 meters, that's about 450 feet. A little more than that because a meter is a little more than 3 feet. So, lesson here is, if you launch something pretty close to straight up at 100 miles per hour, it's going to get to about 450 to 500 feet high before it turns around and drops back down. Look how far away it lands. Close to about a little more than 100 meters away. In reality, it would land more like right here because our velocity changes continuously, not just in these discrete steps. So, what more can we learn about the path of this projectile? Let's go to our equations. So the equations of motion for a parabola, if we look at this one here and this one here, we can say that our change in x, well, we can just write that as x minus 0, because our initial position is 0, we start at the origin. And delta t, we can write that as t minus 0. And delta, because we start at time equals 0. And delta y, we can write as y minus 0. So taking these two equations, I can put them together to get x in terms of y. I'll do that by eliminating time between them. Time, remember, is the bridge between the horizontal part and the vertical part. So I can use time to relate x to y. So our equations are that x equals vxt, and then y equals v1y t plus 1/2, and then there's our y component of the acceleration, t squared. So I can solve for time here. Time is x over vx, and substitute this in for time here and for time here, which gives me y equals v1y x over vx, and I'll take 1/2 times negative 9.8 to give me negative 4.9 meters per second squared, and then times squared will be this squared, x squared over vx squared. Let me rearrange that to say y equals negative 4.9 meters per second squared over vx squared. That's all times x squared. And then this term becomes plus v1y over vx times x. This has the form y equals ax squared plus b times x, where this here is some constant a, and that there is your constant b. That, of course, is the equation of a parabola. That is a quadratic equation, which means that this shape here is, as it appears to be, a parabola. Lesson is that projectiles always move on parabolic paths. That's true for any projectile, no matter how we launch it.